When it comes to the design of any particular lighting module, the topic of thermal management becomes rather essential in order to ensure a high lighting performance. Now, I would like to demonstrate today how SimScale can be used for such analysis via an example of an off-road vehicle headlight analysis similar to the one that we see over here on the top right corner. Now, of course, behind every simulation, there is a question. And the question that the design engineering poses here is, how can I optimize the heatsink to ensure a highlighting performance and, of course, also minimize the LED temperature? For this simulation that I would like to talk about today, we have two different heatsink designs. One of them is made with 9 fins, and the other one with tighter spacing and more number of fins. So we have here 15 fins, and basically this module has 6 LEDs, where each one of these is dissipating 3 watts. Moreover, for this simulation, I would like to demonstrate the SimScale's conjugate heat transfer simulation using the immersed boundary method. The most important takeaway from this is with the immersed boundary method, you really don't have to spend time cleaning up your CAD model. You can run your simulation on the CAD that you bring with minimal or even with no CAD cleanup at all. And that's basically just due to its meshing techniques. And benefiting from the cloud aspect of SimScale, we can of course run multiple different design variations in parallel at the same time. And I will demonstrate that as well later. And essentially, this will eventually lead us to understand how these two different designs operate, what sort of outcomes can we get from it, and so on. Now let's take a look at how this looks like inside the SimScale platform. First of all, we can jump into the SimScale website via your favorite browser. And once you are on the website, you can essentially log in to your account via username and password, and then navigate to your dashboard. Inside your dashboard, you have all of your projects nicely organized inside folders. If you are working with teams in your organization, each team can have their own space where each one focusing on different simulation use cases and so on, and they all can be nicely organized and also managed by an organizational admin. In this case, today, here's the application that we would like to focus on, and now I would like to jump into the results of this simulation and basically start from there. Right. So now we are inside the SimScale platform. So this is the UI, and I'm directly now inside the post processor. You see over here, you have various different filters that you can use in order to extract the necessary information for your design. It's important to know that the pre-processing and the post-processing happens all inside the same tool. You don't have to use different applications for different things. Now, we have here the temperature distribution plotted on the model. And what I would be very interested in getting out of here is what is the overall temperature distribution of or temperature values of these LED chips. So we see over here that we have a minimum value of around 95 to a maximum of around 99 Celsius degrees. And this is for the design with the 15 fins heatsink. I would also be very interested in understanding what is the value, what's the temperature value of the heatsink fins, which we read over here values of around 48 to 49 Celsius degrees. Now I wonder how does this compare to the 9 fins heatsink. And for this, I'll show the results of the LEDs in a different way. Basically, in the preprocessor, you can define some area averages where you can extract the average temperature value on these LED chips. We see over here that the maximum is around 376 to a minimum of 365, which is around 92, 93 Celsius degrees, which is approximately 4 degrees lower than the 15 heatsink design. That's already good insight, right? But we would like to understand why is that the case. And for this, I can compare now the two designs side by side inside SimScale. So on the left-hand side, we have here the design with the 15 fins heatsink, and on the right-hand side, we have the design with the 9 fins. Now, clearly, we see here from the temperature distribution that the 15 fins heatsink design actually does have a higher temperature in comparison to the 9 fins one. So we see here values as we measured earlier around 49, 50 Celsius degrees, where here the legend shows us it's mostly around 44, 45 Celsius degrees. Now we can try to understand this a little bit better by creating a cutting plane where we visualize the velocity distribution inside the fins. interesting is that we clearly see here between the two designs that in the 9 fins design, we have a much higher velocity actually going through the fins in comparison to the 15 fins one. And that essentially improves the overall convection efficiency of the hot air, taking it away from the heatsink out into the ambient air in comparison here. So, and that is interesting because here we have, even though we have a higher surface area, it seems that the convection effects actually are more dominant in this case. Cool, nice. Now we took a look a little bit about the results. We have an understanding about this particular design, but now let's see how we can actually set up such a simulation inside SimScale. For this, I would navigate now back to the main project screen. I'll go ahead and import my geometries. Now, SimScale works with almost all major CAD tool providers, so whether you're using SolidWorks, Inventor, Rhino, CATIA, Creo, etc. Once you import your CAD model, you can go ahead and create a simulation. SimScale is a multiple physics platform, so basically you can run simulations on purely flow or coupled flow thermal, structural simulations coupled with thermal as well, or even electromagnetic simulations. For this case, our solver of interest is the conjugate heat transfer IBM, which essentially couples both the fluid and the thermal side of things and allow you to simulate heat transfer by convection, conduction, and radiation. Once a simulation is created, you get always prompted with the global settings of that simulation and as well with the simulation tree, which is essentially your guide on setting up that particular simulation. So to set up such a simulation, we are mainly interested in a convection effects, right? So we assume that this light is placed on a large air volume. So for that, I would enable the external flow and I would enable radiation as that has some influence on the results, right? And then I would just need to go ahead and fill out this template that I have made for me. First of all, we start by defining the gravity direction, which in this case is in the positive y direction. Then go about setting up the material. So starting first with the fluidic material. So in this case, we have an air volume, which you can create directly in the material setup only for an IBM simulation. Once you have that done, you can go about defining the solids, and here you have a default material library that you can choose from. Of course, you can create your own materials as well, which you can use in your other projects. So for example, we can set up here together one material. So we have here the aluminium for the housing and the heatsink. For the setup of the remaining of the simulation, let's take a look at the simulation that we have over here. So we have here all of the materials defined, the aluminium, the glass, the rubber for the gasket, FR4 for the PCB, steel for the mount, silicon for the LEDs and the components, and finally PP or polycarbonate for the reflector. The ambient conditions that we are simulating over here are 20 Celsius degrees, but we can also run a parametric simulation, which allows me essentially to investigate what would happen under different operating conditions. So here I have a parametric simulation set up from 20 to 40. We can add 45, for example, on a very extreme summer condition, maybe 50 Celsius degrees as well. Once we have that done, the only thing that remains is telling the simulation how much of energy being dissipated from the LEDs, which in this case, 3 watts per LED chip. And that is essentially it regarding the simulation setup. I can go ahead now and run an experiment, which essentially what's going to happen is going to fire off all of these different ambient condition scenarios that I had. All will be running now at the same time in parallel. So if one simulation takes 1 hour to finish, all of these are going to take 1 hour to finish. Now I do have another heatsink design that I would like to investigate, and I could of course just go ahead, create another simulation, do the same setup completely, but if I can save this time essentially and run this more efficiently by making use of this existing setup as a template, and then I can simply swap the geometries between the 15 fins and the 9 fins geometry, and all of the same CAD entities will be mapped to the simulation setup over here. So you see all of the setup had been correctly mapped. You see here from the report. And the only thing that remains for me is essentially just to go ahead and run a new experiment. So now in total, I have 14 simulations running at the same time in parallel, which can only be done using a cloud native solution like SimScale. Now, of course, at any particular stage in your simulation setup, you might get some questions about the setup or any particular question that may arise in your workflow. You can always get in touch with us and write us any message in the chat like, hi, I need help in X and Y. And this is really your reminder that you are never alone when you are using SimScale. Thank you so much for listening.